welcome to Algebra 2 with Mr. Clausen. Today we're going to introduce polynomial function behavior, and really this is just going to be an overview of polynomial functions. We'll start this video by talking about how we classify polynomial functions, function notation, those type of things, and I want to take a little bit of time to talk to you about how to analyze the end behavior of polynomials using really just the classification of the polynomial. So that will be kind of our quick synopsis of what we're going to do. So let's get started. So to go over what a polynomial is really just any type of function that's got variables like this. And polynomials take a huge number of different names. Usually it's a function that has 4 or more terms. Sometimes it gets used as a broad generalization, but really the important thing is we want to be able to classify all types of functions, including polynomials. So we've kind of capped off, you know, looking at, hey, we have constants. This is what you've been working on forever. Early years, elementary school, those type of things. And then we spend a lot of time talking about linear functions. So things that are x to the first power, which we've talked about in previous lessons. And in this last unit, we expand to quadratics. And the term associated with the quadratic is, you know, the -5 is associated with x to the second power. So the x to the second power is what makes the term a quadratic. And the reason we keep track of these is that as you've gone through mathematics, you know that if you're looking at a linear function, you know it looks something like this. And you know when you're working with a quadratic function, it looks something like this. If you're working with a constant, you know, it would just be like y equals 5, and it would just be a horizontal line. And you have some basic understanding what the behavior is going to produce based on what it is. So really, once we get into polynomials, we've been breaking this half of this equation up for a while. So now we're just going to expand it out to other types of functions. So if you have x to the third power, we would refer to that function as a cubic function. So this is a cubic term. Fourth function is a quartic function. So the -3 here would be a quartic term. And then x to the fifth is a quintic term. And these are just different degrees of a polynomial. And whenever you're writing a function in this polynomial notation, you always go from the highest power to the lowest power. All right, so you're always going to put them in order from the highest to the lowest. And the reason is that we want the most important thing first. So if this was an actual polynomial that we were looking at, we wanted to graph it and analyze it, the overall shape and behavior and everything that kind of goes on with the graph would really be dependent on this very first term. So one of the first things that I'm going to do is I'm just going to show you a function here. All right, p of x equals 5 minus 3x, and we're just going to rearrange it in the correct notation here. So we're going to go -3x plus 5. And now this is in standard notation in terms of what a polynomial should be. But we see that this is very similar to what we've looked at really for years. This is just a linear term. So we know this to be a linear function. Most chapter 2 and chapter 3 of our textbook has spent a lot of time looking at this, and then this would just be your y-intercept. So if we want to classify this, we can classify this as a linear function. And then another common thing that we look at in terms of classification is how many terms does it have. This has 2 terms associated with it. And when we start classifying by term, you know, if you're looking at number of terms to, let's say, the name that goes with it. All right, if something has just a single term, you've probably heard this name before. We call it a monomial. If something has 2 terms, we call it a binomial. If something has 3 terms, we call it a trinomial. And mind you, these each kind of get their own name because they're all relatively common, right? And then if something has 4 or more terms, we call it a polynomial. So really what we're going to be looking at in this unit is kind of busting out all the other possible variations of a function, maybe less common, but give you all that knowledge that you need to be able to describe them, analyze them, understand their behavior and those type of things. So we see that there's two terms and that the highest order term is a linear term. I don't care that there's a constant here because the constant's going to be overpowered by the higher degree term here, the linear term. So this would be, by definition, a linear binomial. And that's what its classification would be. Again, now that you've seen an example, let's break down p of x here. If you want to pause the video, you can and try to do this on your own. But if we're looking at this, the first thing I'm going to do is switch these back and forth, because I want the highest power first, because I said it's the most important, so it should be established in that hierarchy. We go negative x to the third plus x. Now these are all placed by order of highest to lowest power. And I can see here that x to the fourth is a quartic term. Okay, so that means that this function is a quartic function, and there are three terms. 1, 2, 3. So that means that this is a quartic trinomial. So the three terms dictates its name, and that is the basic idea of how to classify a polynomial. So again, one of the reasons I want you to know some of this terminology and how we do this for polynomials is because if you know what something is, it gives you a really quick synopsis of being able to go, oh, I identified something's a linear function. So if something's a linear function, you know, when we make a model of that function, what I have here is 4 graphs that use the exact same set of data. So what we can do here is that if you have a linear model, all right, you have this linear line. And what you'll see is that as you go from negative infinity, you start down, and then as time progresses, you go up, right? Because it has a positive slope. And you can get an equation for that line. You can get an r squared, which is a pretty good r squared. And anything above 0.9, I think, is reasonable to assume some type of relationship. 0.9 is better. 3 nines is amazing. So, and we've talked about linear models. Now, if we're talking about quadratics, you've seen a lot of these. You make a parabola, so you get this curvature to your graph. And the more curvature you tend to add to your graph, the better that you're usually able to match the trend line to all of your data points. So as a consequence, your r squared usually goes up. Now you have to decide whether you want to go with the more complicated model for the amount of r squared that you gain. Generally, the lower order model, the better in terms of like extrapolating and using it for like real world applications. But, you know, if that's what you need to do to get the better r squared value, that's something that a lot of people usually want you to do. Usually if I'm asking you which model best fits the data, I'm asking you, you know, should you use the quadratic or the linear? In terms of which one fits it better, it's the quadratic in this case. Now, if we go to cubic, this is one you haven't seen yet. And this is where we're kind of opening up the world of polynomials to you, is that you'll see that the shape of the cubic model is totally different. So, you know, you start, sorry, this is up. And you, as you go from negative infinity on to positive infinity, you start up, you have one curve, you have 2 curves, and then you go back down. And this doesn't look anything like a quadratic. It doesn't look anything like a linear. And that's because the x to the third power dictates the behavior, right? Where the quadratic was up and up because it was an even power. You know, a cubic model would go up and down because it's a negative polynomial here. If this was positive, then it would switch and you would start down and then go back up. But you would still have kind of this squiggle behavior in the middle, and that's because that's defined by the cubic model here. That's what makes the squiggle, is the cubic portion of the model, the x to the third power. So the power of the polynomial, or the degree of the polynomial, dictates the behavior. So if you can classify, hey, this is cubic, oh, this is quadratic, oh, this is linear, you're able to already get a sense of what the general shape of the polynomial is. The last one I'll talk about here is I'll just look at a quartic model. So here I have x to the 4th power. And if I'm looking at x to the 4th power, I start up, because it's a positive quartic model. Have 1 curve, 2 curve, 3 curve, all right? And you'll end back up. And you can see that, you know, my regressions for all of these get more and more complicated as I increase the degree, but my R-squared value tends to go up as long as it fits that model relatively. So you can see just understanding what type of polynomial we're working with can give you a general idea of shape, and I want you to be able to have a general idea of shape because you can graph things and be like, oh, that looks right, that looks weird, why is that not really lining up to what I think it should be? So now that I've gotten a chance to show you some basic classification, that type of thing, what I wanted you to be able to do is that if you can identify something as a cubic or quartic polynomial, you can get a quick idea of what the end behavior of that polynomial will look like. So I have a couple polynomials here in standard notation. So for example, what you could do is that if you are looking at this polynomial, you can see that this is a cubic trinomial. And with this, we can either have a situation where we have a cubic function that looks like that, or maybe a cubic function that looks like that. You know you'll have kind of this wiggle in the middle because you have x to the 3rd power. And because it's an odd function, one thing that you'll notice is that you'll either start down and end up, or end up and then finish down in terms of that notation. And really the idea, if you're trying to analyze what the end behavior of a polynomial should be, really all I'm asking you to do is go, if x approaches negative infinity, what happens to this function? So if we say p of negative infinity, all right, and what's going to happen here is that if you have negative infinity, and you cube that, we could plug in the other parts there, but the fact of the matter is that if this cubic term is going to infinity, this is going to get to a higher level of infinity faster than the x squared. So really we can ignore all the lower powers, which is why these higher order polynomials dictate the shape of everything, and why this first term really tells you the majority of the information that you need to know about a polynomial. And really all I'm trying to do is when I'm looking at end behavior, it's like, all right, is it finishing off in the negative direction, and where is it starting? And all you need to know as far as trying to figure that out is whether the function will be positive at negative infinity or negative at negative infinity. And the fact of the matter is if you have a negative number and you take it to the 3rd power, it's still going to be negative. And if you take a negative number and you multiply it by the minus sign that's on the outside, that's going to make it a positive value. So as you approach negative infinity for this given function, you're going to start with a positive up type behavior. And as x approaches positive infinity, wouldn't necessarily have to do this, but I think it's good to just do this as you're getting started. If you go negative and then you go positive infinity to the 3rd power, what you're going to have is that take a positive number to the 3rd power, tell you what, it's still going to be positive, and then you apply the negative sign to it, it will be negative. So you'll end with a down behavior. And all that means is that when you're looking at this graph, you'll at x and y, this would be the negative side, this would be the positive side, and as you start from negative infinity, you'll start up. As you approach the positive infinity direction, you'll go down. So your graph will look something sort of like that. And you can already anticipate what the overall behavior of this function is going to be. And it's just going to be up and then down. Just like I told you, one of the possibilities would be right here. And that's all I would ask you to do in terms of analyzing end behavior. It's going to be, you just say it starts up and then ends down. All right, in terms of looking at that behavior. Let's look at one more. So right here we have a quartic function, a quartic monomial, to be specific, And again, I'm going to do the same test. If I plug in negative infinity, p at negative infinity will equal negative infinity, that whole thing, to the fourth power. Well, you take any negative number and you multiply it 4 times, you're always going to get a positive number. And again, since it's an even polynomial, like 2, 4, 6, 8, we know they're both going to be pointing in the same direction, but I'll just show you here. If we go positive infinity to the fourth power, hey, guess what? You take a positive number to the fourth power, it'll still be positive. So again, what that tells you is that you're going to have a up, then up behavior. You start up, you end up. All right, and for this, you know, it might look something maybe like this. And then you have your first curve, and then you have like a second curve, and you have up and up. And as you gain more familiarity with these polynomials, you'll see, you know, as you have maybe some of these lower terms, you'll see how it shifts it or maybe stretches it or narrows it or those type of things. But really, we're just looking at, hey, now that we're exploring polynomial functions, what are some of the basic end behaviors that you see? What are the general shapes of these different polynomial models, and how do we extrapolate on that? In the next video, I will show you how to do regressions of these functions, and then you can start graphing them and looking at some of that and making these models on your own. So I hope this video is helpful in kind of introducing you to polynomial functions, and I hope you have a great rest of your day. Peace out.